keeping on with probability, we're going to look at the counting rules right now. We're going to take a step back from probability, and we'll look at that at the end of this lesson, and let's just get some setup going on here. Well, the first thing we're looking at is what's called either the basic counting rule or the fundamental counting principle, both kind of the same thing. And here's a definition for that. This is an official definition. I would spend a lot of time memorizing the official definition, but if we look at a few examples, it's going to make a lot of sense. So our first example, James and Carol are building a house. They have three choices for the front of the house, whether they want brick, stone, or siding. Then they have two different choices for the windows, shutters, or no shutters, and they have three choices for the front door. Well, the question is, how many different houses can they develop from that? Well, you can either look at this through the formula, or you can think of it as a tree diagram. Either way, there's three choices for the front of the house, two choices for the window, which gives them six choices at that point, simply 3 times 2. And then of those 6 choices, they can pick either one of the 3 doors each time, 6 times 3, which is 18. So there's 18 different ways they can figure their house. Looking at a little larger problem, which is dealing with the university here, and they're going to develop IDs for their students. It's going to end up being 5 characters on the ID. The first 2 are letters, and the first one has to be a vowel, the second one has to be a consonant. And then there's 3 digits behind that, and originally we're going to say that those numbers can be repeated. So you might have 111, and that'd be fine at the end of the ID. So the first thing we do is we put the 5 out there, because there's only 5 choices for the very first one. It has to be one of the 5 vowels. Then there's 21 choices for the second location, and then because I can have repetition, there's 10 choices for each, the third, the fourth, and the fifth character. That gives me 105,000 different student IDs that are possible. What if the university changed their mind? And they said, you know what, we don't want to have repetition. Similar idea, but instead of the 10, 10, and 10, well, now there's only 9 choices for that second digit because one's been removed. And there's only 8 choices for that third digit. And look what happens to the number of IDs that are out there. We now have 75,600 IDs that are possible. This is an important thing, is if you're a major university, you may have a lot of students, especially when you bring in the grad students and the part-time students and the doctoral students. Is 75,000 enough? If you're going to allow students to repeat after a certain number of years, for example, if a student graduates 2012, when can their ID number be used again? Is 2013 okay? Is 2014 okay? This is something university would have to keep in mind. We talked about factorials before, and you know these from algebra too. All a factorial is when you see that exclamation point. If you're looking at a number like 5 factorial, it would just be 5 times 4 times 3 times 2 times 1. And if you look down here, again, official definition for that. Let's move on to permutations. Again, you've seen permutations before, but you may not remember them. Permutations and combinations have one major difference. In a permutation, order matters. Let's look down at the example. So we're talking about this thing. We're taking the 3 letters from the word word. If we don't allow repeat, there are 26 for the first, then there are 25, then there are 24. So using the basic counting rule, we just do 25 times 20, 26 times 25 times 24, and we get 15,000. Well, let's look at a permutation for a second. If we think of permutation, when we know the order matters, well, now we're going to pick, there's 26 letters we can pick from, and I want to pick 3 of them. So all I'm going to do is my M value in this case is 26, it's my total. The R is the amount that I want to select, so that would be 3. And you look down the bottom of the page, there's my setup. We have 26 factorial over what's going to end up being 23 factorial. Well, the nice thing about permutations, and the reason we could just do 25 times 26 times 24, is because we're dealing with all multiplication on top and bottom, and we know that canceling is division. The 23, 22, all the way down to 1 shows up on the top and the bottom, and they can both cancel each other out. That's where we end up with just 25, 26, and 24. So here's a few for you to practice. Take some time, go ahead and do those. And here are the answers that you should get. So in the first one, I have 20 objects. I want to pick 6 of them. There's a lot of different combinations there. 27 million and change, almost 28 million. In the second one, I have 8 choices, but I only want 1. Well, hopefully common sense says that that has to be 8. In the last one, I have 10, and I want to pick 10. So let's say you're playing on a slow pitch softball team and 10 players play, and I want to make a batting lineup. Everybody has to bat. Whether you bat first or you bat 10th, you're in the lineup somewhere. So again, there's a lot of combinations here, a lot of possibilities. How many different 4-digit ID numbers can be formed if we don't allow a digit to repeat with an ID number? It's going to be that situation there. Because we have 10 choices and we're selecting 4 of them, and order matters here. 1, 2, 3, 4 is not the same as 4, 3, 2, 1. Do the same thing with books on a shelf, except in this case we want to put all the books up there. So this would be 6p6. The key in that bottom problem is, remember that 0 factorial is equal to 1. So on the bottom, 0 factorial, a lot of people want to say that it's 0. Be very careful with that. Combinations, very similar. Order doesn't matter. Have an official definition, and we have an example there. But let's actually flesh out the definition. All we're basically saying is very similar to a permutation, except notice there's another r factorial on the bottom. The reason this r factorial is there is because a situation like 1, 2, 3, if we put 3 numbers together, or 1, 3, 2, 2, 3, 1, and so on and so forth, they're all the same scenario if order does not matter. In a permutation, they would all be different. Well, if I know that the order is the same for all of them, I'm going to have a less amount of choices. That's why I'm adding something, or in this case multiplying something, to the denominator. The bigger the denominator, the smaller your final answer will be. So down the bottom, look at 20 books, and I want to select 3 of them. Well, if I have 20 factorial on top, and on the bottom I have 3 factorial times 17 factorial, think about what we did with permutations before. 17 down to 1 shows up on the top and the bottom. So just like we did with permutations, I'm going to cancel that out. The difference here is, instead of just having the 20, the 19, and the 18, I still have 3 factorial on the bottom, 3 times 2 times 1. If this was a permutation, those denominator numbers, the 3, the 2, and the 1, would not be there. I'd have 6 times more possibilities. But in this case, because order does not matter, how I select these books makes no difference, I only have 1,140 possibilities. Keep in mind, difference between permutation and combination is that order matters, but instead of memorizing that, you just sit back and ask yourself, would I expect a smaller amount of possibilities, or would I expect a higher amount? If order matters, it's going to be a higher amount. If order doesn't matter, it's going to be a smaller amount, because again, if I pick choice A and then choice B, or choice B and then choice A, they're the same thing in a combination. So a little bit of practice here again. These are the same numbers that we had before when we talk about 20 and 6, 8 and 1, 10 and 10. But now look at my answers. My answers are getting considerably smaller in this case because order does not matter. Again, we're putting more numbers in the denominator. By putting more numbers in the denominator, my answer is going to end up being smaller. Some problems with combination. I want to talk about how many different 5 poker hands I can have from a 52 card deck. Order doesn't matter. So when you play poker, there's about 2.6 million different hands that you can get. If I have a group of 25 people and I'm selecting 8, assuming that the people do not have different positions in the committee, it would look like that, and there's a little over 1 million different committees that can be formed. Let's look at arranging these letters in the word Austin. Well, in the word Austin, if I want to rearrange those letters, I have 6 choices for the first spot. Then I have 5 choices. Then I have 4 choices. This is just a factorial. Same thing with Columbia. When you get down to Lincoln and Atlanta, they're a little bit different. And the reason that Lincoln has the 2 factorial and the 2 factorial on the bottom is simply that the letter L shows up twice in the word Lincoln, and the letter N shows up twice in the word Lincoln. So I need to take into account that whether I put the L first or second and the other L first or second, those are going to be the same string of letters. If I look down at the word Atlanta, The T shows up twice, but the A shows up 3 times. There's still 7 choices. There's still 7 factorial on top. But now since there's 3 A's, if they're all in different locations, I'll never notice because they're the same letter. We're talking about 3 factorial on bottom, and because of the 2 T's, 2 factorial on bottom. So if you have letters that are doubled up, you need to take into account what the denominator is going to be. And that brings us to taking this idea and bringing it back into probability. And let's look at a couple examples here, or one example. So we have 15 people in a club, 8 of those are boys and 7 are girls. And we're going to pick a club or a committee that has 4 people in it. Well, if I take the 15 students and I choose 4 of them, order doesn't matter because they're all part of the same committee, there's going to be 1,365 different committees that can be developed. Well, then my question is, what's the probability that the committee will have all boys? Well, in this particular case, you have to figure out what's the probability that of the 8 boys, if I select 4, again, order doesn't matter, how many different scenarios are there? How many different possibilities are there? Well, that's just 8C4. 8 choose 4. It's a combination. So I end up with 70. Well, that's 70 possible out of the 1,365. So the probability is about 0.05 rounded off. I do the same thing. What if there's 4 girls? I find the amount of committees that have all girls. There's 35 committees that have all girls and no boys. Divide that by the 1,365 and you end up with about 0.025. If you wanted to round it off to 0.03, that'd be fine. The key here is the sample space written out would be the 1,365 different possible choices. 35 of them would be all girls. Same scenario, but what if we're looking at 3 boys and 1 girl? Well, now we have to take into account, if you look at the answer to this, we have 2 different parts to this. We have 8 choose 3, and we have 7 choose 1. Well, the 8 choose 3 represents how I'm going to pick the number of boys. The 7 choose 1 is how I'm going to get the number of girls. When I put those together, there's 56 committees that have 3 boys, 7 that have 1 girl. I multiply those together, so there's 392 different possibility groups that have 3 boys and 1 girl in them. Do a little division. There's a 0.29 probability that I'll end up with a group that has 3 boys and 1 girl. Down the bottom, I do the same thing, but now it's 3 girls and 1 boy, so the 3 and the 1 get switched. The 1 now goes with the 8, the 3 goes with the 7. There's 280 different possibilities here, so the probability is 0.21. Since there's 5 possible scenarios here, 4 boys and no girls, 3 boys and 1 girl, 2 boys and 2 girls, 3 girls and 1 boy, or all girls, if I took the 4 situations that I have, the only one I haven't taken care of is 2 and 2. The remaining probability that would get me up to 1, I don't have to go through this process for the 2. Could if I wanted to, but I don't have to.